Clap once if you could hear me. Twice if you could hear me. 3 times if you could hear me. All right, so we're going to have to move a bit fast today. Discussion session might have been a little bit discombobulating. If you went to discussion, you did RSA before we did it in class. So we're going to have to speed up a little bit. We spent, I think that's on full, yeah. We spent quite a bit of time looking at this yesterday, or Thursday, trying to figure out how to cancel an exponent. And honestly, where you all were was very confused and thinking very hard, and I think that was perfect. That's my comfort zone, but we simply don't have time for it. So we're going to briefly go back over that, because that is the key to understanding how RSA works. And then we're going to cover RSA today and the beginning of polynomials. We won't go over secret sharing today. I think that's reflected on the syllabus now. We'll go over that Thursday, and that's already been reflected on the discussions and homeworks that's been pushed. So today we're going to try to get you RSA and polynomials so you're ready for homework. So yeah, today might be a little bit faster, but yeah, I think we'll start with a warm-up. Great. Are we good for cameras? Awesome. Thank you. Okay, yeah, so warm-up, per usual. This one's a little bit weird to start with. We're just saying simplify. We have x to the 81, and it's mod 11. So, yeah, if you don't see it offhand, it'll be a little bit tricky, but does anyone see how we might simplify this? Yeah.
It's x to the power of 80 times x. And you know x to the power of 80 is x to the power of 10 to the power of 8. So that should be 1 times x, which is x mod 11.
All right. So we're getting a claim that x is congruent to x. Yeah? Mod 11. And does anyone know what theorem is being used to find this? Yeah. Yeah. So this comes from Fermat's little theorem. That's written all the way over on the right-hand side there. We've seen that a few times now. But it just, if we have a prime, then x to the p minus 1 will be congruent to 1. So where do we get this from? Let's take a look. X to the 80, like was being said, it was just broken apart for us, is x to the 81 is x times 10 times 8 plus 1. Well, first off, what is Fermat's little theorem? In this case, it's going to be that x to the 10 is congruent to mod 11. That's Fermat's little theorem because 10 is just 11 minus 1. Right? We can just write that. 10 is equal to 11 minus 1. So we have x to the 10 times 8 plus 1. We can break that apart. And this right here is 1. So this is just x. I ran out of room to say mod, so we'll say it right there. And do we want to move up there yet? No. So the key point here, though, is if I have anything like that, if I have x to the 10 times k plus 1, that's going to be x to the 10 to the k times x, and that will be 1. So anytime, this will be equal to x to the 1, mod 11. And the trick that's happening here is we kind of have two moduli kind of going at the same time. On the ground floor, we have mod 11, but at the same time, we're having something happen up here in the exponents, and that's mod 10. 10k plus 1, that 10 is where we wrap. That's where we go away. So even though we have mod 11 up here, because of Fermat's little theorem, we have a mod 10 up in the exponent land. So we'll look at one more thing. Or to really get the idea of this, how do we simplify x to the 93 mod 11? Yeah. This will just be the same as x cubed, right? because x 93 is really x to the 10 times 9 plus 3. This 10 is 1 for Fermat's little theorem. So the real point here is that, again, we have mod 11 down here, and up here, we have mod 10. 93 mod 10 is 3. So this is the kind of crucial point to understanding how RSA works, that there's two moduli happening, and when we're trying to solve things in the exponent, by Fermat's little theorem, we're going to have p minus 1, which in this case, 11 minus 1 is 10. There's a new exponent that we're dealing with up in exponent land. We are moving a bit fast. Hopefully we have a bit of shelf space in our head already for this, because we have thought about it quite a bit on Thursday, I guess it was. And what we did Thursday was solve this. We spent a bit of time solving this. And really, the idea was exactly what we were doing up there, right? We were trying to find what d can I raise this to, because I'm trying to cancel the exponent. So if I raise it to d on both sides, what lets me cancel the 7? So really, we're trying to solve for x. That's mostly what we're trying to do in algebra, solve for x. So what d can I raise it to so that I cancel those exponents? And we spent a lot of time thinking of that, of like x to the 7d. What we want that to be is we want it to be x. That cancels the 7. And really, x to the 1. So where's my colors? Here we go. And the way this works is, again, down here, we have mod 11. Up here, here's my 1. We have mod 10. So we're trying to find d times 7 that gets us 1 mod 10. Really, all that's happening in exponent land is we're trying to find d such that this is true. And this should look more familiar. No, not. This should look more familiar because we know how to find multiplicative inverses. We're trying to find the multiplicative inverse of 7. 7 times what is congruent to 1? And this is what we did last time. We found out, oh yeah, d would be 3 for that to work. Because 3 times 7 is 21. Mod 10 is 1. And, you know, we made a whole show about it to be like, okay, well, x is equal to x to the 20. And x to and this goes away to 1 by Fermat's little theorem. Right? This is where FLT comes in. And if we did that to both sides, then we get 3 to the 3 over there. And you know, solving that, that's 27, which is congruent to 5 when we're dealing mod 11. And then, you know, we had a little celebration, and I said, like, oh yeah, look, we found 5. That's the x in mind. So this is just a recap. The main point is this. We have one modulus down here, another modulus up here. This is going to be the key to understanding RSA. Any questions about this before we talk about what RSA is? Yeah?
So we're looking at x to the power of 7d, and then we know that's x to the power of 21. And then we know that x to the power of 10 becomes 1. Where did 3 to the power of 3 come from?
Oh, that's me raising both sides to the power of d. That's saying raise, well, d in this case will be 3. So we found that d is 3, so I'm raising both sides of the equation to 3. That is x to the 7, raise it to 3, and 3, I also raise it to 3. That's me solving for x. Does that make sense? Yeah. So this was just the right-hand side of the equation. There's kind of like left-hand side, right-hand side there. Right. Okay. So that's the context we need for understanding kind of how RSA works on a fundamental level. And then we started talking about, you know, what is cryptography. And what we got to is describing what secret key cryptography is. And there's 3 players. There's Alice, Bob, and Eve in the middle trying to eavesdrop on everything. Right? So we have Alex trying to send some message X. And the idea of secret cryptography is you can encrypt it with a secret key, and then Bob, having the same secret key, can decrypt it. So this is just what we kind of talked about last time. And what we want is that the encryption and decryption algorithms are easy. If you have the secret key S, you can just compute them. But X is hard to recover from Y if you don't have the secret key. So this is the fundamental idea of what secret key cryptography is. And now we're just kind of caught up with where we are on Thursday. And now we can talk about what RSA is. Yeah. So this is called secret key cryptography. Sometimes it's called symmetric key cryptography. Symmetric because Alice and Bob both have the same secret key. It's symmetric. They share a secret, and that's, it's like if you lend someone, if you have a lockbox that only you and your friend can open because you share 2 secret keys, then you could put messages in them, lock it, and send it to your friend, and they can unlock it. That's symmetric key cryptography. There's 2 problems with this. One is, what is actual hardness? The problem is that people have been doing secret key cryptography for as long as we have history that we know about. People have been trying to encode messages so that they're hard to read, and people always break them. Cryptography always has this big boom when in wartime, empires are trying to encrypt data so that communications can't be read. And when you have a whole empire trying to break your encryption scheme, they usually break it. Right? So secret key cryptography has been broken over and over and again throughout history. There's something called Schneier's law from Bruce Schneier. He's an applied cryptographer. The quote is, anyone can create a crypto system so clever that even they themselves can't break it. And that's the problem, is like, yeah, you can fool yourself into thinking, wow, this is so clever, no one can break it, I can't break it, and then someone else comes and breaks it. So how do we quantify hardness? How do we talk about something being fundamentally hard, or at least base it on something a little bit more solid than just seems hard to me? The other problem is, well, let's say Alice and Bob have never met. Alice just finds Bob's email on the internet and wants to send Bob a message, but wants to encrypt it. What's the problem? Any thoughts? Yeah. Yeah. For symmetric key cryptography, they both need to share a secret. If they've never met before, if they've never communicated, how do they have that shared secret? So the other problem is how to share keys. If, you could send them a secret key, but you can't encrypt the secret key because you don't have a secret key to encrypt it with. So you kind of get in this trouble where, like, you almost need to meet in person and kind of agree on a secret key. And we're going to solve both of these, or at least address both of these, with number theory. So this is quite surprising that that you can use number theory, the math we've been doing this whole time, modular arithmetic and so on, to really kind of make revolutions in cryptography. This is part of modern cryptography, what we're about to talk about. In fact, G.H. Hardy, he was a mathematician at Oxford. He's the one who Ramanujan, the mathematician, first contacted. If you know Ramanujan, there was a movie on him and such. G.H. Hardy has a whole essay talking about, like, the beauty of math for aesthetic purposes, and that number theory is one of the few things untainted by application. It hasn't been used for anything. It's just aesthetic. And then, like, some decades later, modern cryptography comes along and actually uses number theory for some of the most applied infrastructure throughout. Every time you send an email, you're using what's called public key cryptography. So let's talk about what public key cryptography is. It's kind of this magic thing. It almost seems like it might be impossible, and then you do it. So what's going to happen, we still have the same players, Alice, Bob, Eve, listening. But instead of having one secret that both people share, where do I want to write this? you have what's called a public key and a secret key. Another way to talk about public key cryptography is asymmetric cryptography, where you're no longer symmetric. You have two different people that have two different sets of information. So Bob now has what's called a secret key. I'm going to say SK for secret key. And Bob puts out a public key. Public key, PK, and both Alice and Bob get that. In fact, all of the world gets it. Bob just throws out the public key for everyone to see and keeps the secret key for himself. So now what happens is that when you encrypt a message, you can encrypt it with a public key, and only Bob can decrypt it. D of y, mixed up my variables there. X is equal to d of y. And Bob is using a secret key to is using a public key to encrypt. It's kind of a magic thing. They never shared any information. They don't have any shared secret together. But there's this kind of thing where, yeah, you can have a public key out in the world so that only Bob can decrypt with the corresponding secret key. If you just looked at this definition to begin with, it might seem kind of impossible or improbable. Like, how would we do such a thing? One way to make this make a little bit more sense, at least metaphorically, is instead of thinking of shared secrets where there's a locked box, you could think of Bob making a padlock. You know, a padlock you could just kind of close. And he puts out the blueprints for the padlock into the world and keeps the secret key for himself. So with that, anyone that wants to send a message to Bob can just take one of the padlocks that's out in the world, lock it onto a box, and only Bob can unlock it with his secret key. So metaphorically, kind of how we can think of it. A padlock, this is the key to all the padlocks that are out in the world. We'll need to see a concrete example for that, but are there any questions on the idea of public key cryptography offhand? Yeah, so now we get back to problem one, actual hardness. How do we know that something is actually hard? We'll argue, yeah, the padlock example, you might think that you can reverse engineer it, and with number theory, we're hoping we're dealing with fundamentally hard problems where you can't reverse engineer it, and we'll talk about what hardness means in the scheme we're about to come up with, RSA. Yeah? Yeah. Yes. Bob creates both the secret key and public key pair. Bob creates public key, secret key, throws public key out into the world, and keeps secret key to himself. Right. So that's the model. Bit of a surprising model, and yeah, this is basically the same. One thing I do want to note is secret key is called private key in the notes. I'm calling it secret key so I can have PK and SK and those be distinct. Public key, secret key. Okay, great. So yeah, I guess the first thing to talk about is what is actual hardness. We don't need that anymore. Yeah, that's gone. Okay. So actual hardness, this is where math comes in. Math has structure, and you can build things from structure. So this is why math is useful. One thing to note is secret key cryptography existed as long as we've had history. We know about secret key cryptography since as long as we've had history. Public key cryptography, 80s. This came about in the 80s. Maybe late 70s, depending on who you're asking, but public key cryptography didn't exist until the 1980s. This is very recent, and it comes specifically from number theory. This was a revolution in cryptography. Most of what we talk about with cryptography now is modern cryptography, like kind of 70s, 80s onwards. Okay, so hardness, I'm going to ask a little question first. You have a choice. I'm going to say if you were put in a room and you had to do these as quick as you can, and you were timed on it, which would you rather do? Who would rather factor this number? Who would rather multiply these two? Yeah, Right. Multiplying's easy. We know an algorithm for it. We could plop it into a calculator. Factoring, I'll tell you what the factors are right now. This is 37 times 29. That would have taken me a while to find. You know, like there's not really a clean way to do it. You kind of have to just try numbers. There are some algorithms, but they're not great. You know, like for the most part, brute force search is kind of the best you could do for factoring. So there's a sense that factoring is harder than multiplying. And unlike someone coming up with a clever crypto system, if something is based on the hardness of factoring, that is, factoring is harder than multiplying, that's a question people have looked at kind of since as long as people have been doing math. So if you base hardness on something like this, that factoring is hard, you have a better sense of when something is actually hard. Okay, so let's just talk about what this scheme is. I don't need these anymore. Factoring is kind of the key of it. That's a little messy to read. Okay, we can rewrite that. So first off, we want a secret key, and we want a public key. And to start with, a secret key is going to be P and Q that are prime. We can start seeing how number theory comes in here. And the public key is going to be P times Q. That's how we start it. So for the public key that goes out into the world, we can give N P times Q, whereas Bob, yeah, let's rewrite this a little bit. That's a little messy. Bob has secret P and Q. So far, we have something asymmetric. We have the question that was asked earlier of like, can't you reverse engineer it? If you're given the padlock, can't you reverse engineer it? Well, if factoring is hard, then no, right? Having P and Q makes it easy to find N because multiplying is easy. But if you're just given N, it's hard to factor into P times Q. This is an assumption. We don't have a proof that factoring is hard, but this is an age-old assumption. It would, not only would you break a crypto system if you were able to factor, you'd have, you know, like a Fields Medal. You would write a paper about it and become kind of famous mathematically. So this is how we start. Let's actually create an encryption scheme from it, though. So what is y equal to? There's another part to the public key that Bob will produce, and it's going to be an encryption exponent. So what happens is Alice is going to do x to the e mod n. That's the encryption, is taking an exponent, raising it to that, so the public key also has e up there. So how does someone send Bob a message? They use the publicly generated n and e, and they just compute the exponent. They say x to the e mod n, and then Bob receives that. And now we need to figure out how Bob can decrypt. Where do I want to write this? We can write it here. Yeah, we can write it here. Okay. No, let's write it over here, actually. This will be better visually. That was a hard one. Right. So now let's say Bob wants to do, get a better chalk. What Bob wants to do is cancel that exponent. Right. Bob wants to just find x on its own because that's the message. Right. So how does Bob cancel that exponent? Well, Bob needs to find some exponent to raise it to so that e and d cancel. This should start looking a little familiar. This is why we spent so much time on what does it mean to cancel exponents. So x, we want that is just x mod n. We want something that does that is down here. Down here we're working mod n. My red. Up here up in exponent land, we want e to the d, e times d, to be 1. What's the modulus up here? What's that? Yeah. So n minus 1 is exactly what we were doing for Ma's little theorem. Yeah, we have, we haven't talked too much about our cheat sheet over here, but over here we have Fermat's little theorem, which is if p is prime, then x to the p minus 1 is congruent to 1. Right? So there's a slight caveat here because we don't have a prime p. Right? So we don't have a prime p. What we do have is this special case, though. We have p and q such that n is equal to p times q. And this is what we talked about last time, is this was the Euler's-Toshin function, which was a little bit too much to look at. But we have this special property that because the number of multiplicative inverses mod n is going to be p minus 1 times q minus 1. So there's two theorems here. There's Fermat's little theorem, and then there's x to the p minus 1 times q minus 1 is congruent to 1 mod n. So we went over this last time, and it's a special case of if you have more than 2 prime factors, you have to write a whole new thing. But for just 2 prime factors, we know that this is the new Fermat's little theorem. So n minus 1 is the exact correct pattern recognition for how we were doing everything over there because we were dealing with primes. Because n is equal to p times q, the way to use that theorem over there is p minus 1 times q minus 1. So this is when, like, the theorem is congruent to 1. That's the theorem that's written over there. You have to make sure that, right. You have to make sure that x isn't 0, because 0 can't ever go to 1. You want x to be relatively prime to n, but this is generally true. You could see the caveats over there. So really what's happening is, again, I should have written a mod there. This is mod p minus 1 times q minus 1. So we have two moduli. On the bottom, we have modulus n. On the top, we have modulus p minus 1 times q minus 1. We're going fast here, but this is everything that we did over here, where we're dealing with one modulus down below and another modulus down above, up above. In the case of p being prime, it's just p minus 1. In the case of n being composite of 2 primes, it's going to be p minus 1 times q minus 1. So what we're really looking for is what's happening in the exponents. We want e times d is congruent to 1 mod p minus 1 times q minus 1. So there's one part left to the secret key, and that is find the decryption exponent, which is going to be the inverse of mod p minus 1 times q minus 1. This is what we do. So like if Bob wants to decrypt now, all he has to do is take y and raise it to d mod n. We'll argue about the correctness in a moment. One last caveat is, when does d exist? This is the multiplicative inverse of e. When do we have a multiplicative inverse of e? Yeah. Yeah. We need e to be relatively prime to p minus 1. That's when we have inverses. So we'll just make one last caveat here, and we've fully constructed the RSA crypto system, which is e such that GCD and p minus 1, q minus 1 is equal to 1. That is, e is co-prime to p minus 1 times q minus 1. So we're going to do a few things here. We're going to show that Bob can do this easily and it's correct. And then we're going to argue why it's hard for anyone else that doesn't have the secret key. Okay, great. Yeah. So, yeah, let's argue for correctness. If Eve sends y, which is x to the e, what happens if we raise this to the d? Right. Yeah.
Isn't D equal to that E inverse mod P minus 1 times P minus 1 and GCD of E and P minus, like, aren't those the same thing? Like, aren't they basically saying the same thing?
Saying the same thing. So E is saying choose an exponent that has inverses, and this is saying find that inverse. So one is public, one is private. So E being public, it's just saying that we need to choose an E that has an inverse, otherwise we can't decrypt. We need to have something to invert it by to decrypt in the first place, but that isn't being published. And I guess one thing is, how do we find this? Like, if we have E, how do we find the decryption exponent? We have an algorithm for that. The algorithm we use for that is the extended Euclidean algorithm. So that's the algorithm that we went through that finds inverses. So let's finish writing up here. So again, we have y to the d, x to the e. So now we have x to the ed. And what we want to claim is that this is x to the 1, mod n. And the reason that works is, once again, because down below, we're working mod n. And up above, we are working mod p minus 1. I'm going to erase this now. P minus 1, Q minus 1. That's what's happening up in exponent land here. Why? Because of this. Because of the extension of Fermat's little theorem. The extended Fermat's little theorem says x to the p minus 1, q minus 1 is congruent to 1. And what we did is we said E times D should be congruent to 1, mod p minus 1, q minus 1. That's how we set it up. Set this. This is what's happening in exponent land. E times D is congruent to 1, mod that. Any questions? So this is the correctness of the algorithm. That is, Bob, when they raise it to D, does actually get x back. All right. So this is the crypto system. We'll argue about hardness in a moment, but the main thing to note is, well, in homework, there's not too much to do with the RSA crypto system because it's just there. You'll work through an example, and then most of the problems you get are little tweaks to the system that can be broken. And then you're supposed to show how the whole scheme can be broken if there's any little tweaks there. So that's what to expect on the homework, is understanding this is useful, but also you'll be given a bunch of things that are just slight tweaks of this and are not this. So that's what to expect. Great. And then the last thing we want to say is hardness. And how we want to talk about that is this game that we talked about last time. This is what we solved, right? This is what we solved all the way on the other board, which is if you have a prime p, then you could just find d and then cancel to find x. You can cancel those exponents. That's what we did. When I said, well, tell me what x to the 7 congruent to 3 is mod 11, you didn't need any secret key or anything. You're just like, oh, I can find out what d I can raise both to cancel that 7. What's a little scary about that is like, well, that was easy. What if this is easy too? What if someone can just break the crypto system? Because the game is given x to the e, p, and e. Can you find x? And RSA is very similar. The RSA game is given x to the e mod n x to the e mod n, n and e such that GCD of e and p minus 1, q minus 1 is equal to 1. The game is to find x. And there's really not much to say here other than that we think this is hard. That's kind of the crux of it. The nice thing about this, though, is instead of thinking that, like, ooh, I created this clever little system that, like, swaps the first letter and the last letter and does all this sort of stuff and think that's hard, this is a very simply stated mathematical problem. People have been looking at this for decades and they haven't found out to break it, and we might have decades longer where we still haven't found out how to break it. So this is a very, very simple, clean mathematical problem, and the question is, can you do that? If you're Bob, you know the factors and you know P and Q. If you know P and Q, then you can just compute D. Right? We know how to find inverses because we know what P minus 1 times Q minus 1 is. If you don't know what P and Q are, all you're given is N and E. Good luck trying to find out what D is without knowing what P minus 1 times Q minus 1 is. This is all we want to say on RSA. This is the system. Any questions about it before we move on to meals? Yeah?
How can we find the E that satisfies the condition if we don't know P and Q?
That's right. How do you find E or D? E. Yeah, how do you find E if you don't know P and Q? You don't. This is what Bob publishes. So Bob chooses some E that's relatively prime to P minus 1, Q minus 1, and throws that into the air and lets everyone seize it, and then computes D for himself. Sorry, that should have a D in there as well. So Bob's secret key is P, Q, and D, or it could just be P and Q, and you could always compute D whenever you want. And what's in the air is the P times Q and E. But no other person should be able to compute what E or D are on their own. That's what Bob computes himself and puts out into the world. Any other questions? Yeah. Sorry, what's that? So P is not equal to Q. Yeah. P and Q are two separate primes. Thank you. Yeah. All right. All right. That went fast. Hopefully we had enough shelf space to kind of put things there because we've worked with canceling exponents. Yeah. Yeah. Uh-huh. Yeah. So this here was just to show how you would solve it. If you find E times D congruent to 1, what that means definitionally is that E times D, where'd my chalk go? What that means is that E times D, this is the definition of E times D being congruent to 1, mod P. So E times D being congruent to 1 means E times D is a multiple of P minus 1 with a remainder of 1. So we just plug that into there and see that, oh, look at this. This right here cancels to 1 by Fermat's little theorem, and all we're left with is x. So yeah, that was just some extra scratch work to show like how that process goes. And what's our time? Okay, great. So let's move on because we have homework to prepare for. Questions? Okay, great. All right. Any last questions before we move on? Great. So I'm going to claim that all of you probably know what polynomials are already, even if you haven't seen a formal definition. And we're going to test that real quick. So 4x cubed minus 7x plus 2. So my question is, which of these are polynomials? And we're just going to go through them one by one. And Okay. I'll do the clap one more time. Clap once if you can hear me. Twice if you can hear me. Thanks, everybody. So, real quick, just lightning round. Which of these are polynomials? Polynomial, yes or no? Okay, I heard a little bit more confusion on that one. So we're right that this is no and this is no. Let's give a formal definition of polynomials. We do have the intuition. We've worked with polynomials kind of our whole mathematical life. So let's talk about what they actually are. And all polynomials are of a certain form. Like a polynomial is something about the form of a function. And a polynomial is always going to be of the form a to the d times x to the d plus a to the d minus, oh, I have enough room there. So I'm going to do this. I don't think we need to talk about multiplying and anymore. So what is a polynomial? It is something that looks like this. We have coefficients of x to an integer, and we can have that any power that we want. X, a1x plus a0. And we have special things that we call these things. So let's write it in a different color. Degree is the highest power. We have what are called coefficients. And those are just the constants that are in front of everything. And, you know, you could have different terms for the, you know, constant term. But the idea is all polynomials are of this shape. You could write it if you want in summation notation, if you like that notation. But in any case, x to the I, and that goes from I equals 0 to d. Right. So this is another way to write it if you like summation notation. Really, we're just kind of adding up a bunch of some powers with coefficients in front. So just to make sure we understand this, this function right here, it's degree, everyone? Yep, we understand it there. There, the degree. If I were to ask you what, that's a coefficient. Can someone tell me what A3 is? 4, great. Yeah, we'll just do another one. A0, 2. And here's a little bit of a tricky one. So think on it for a second. A2, show me on your hands what that is. Seeing lots of zeros, a little bit more confusion there. But A2 is 0 because there is kind of this implicit, there's no x squared term here. That's the problem. We kind of have this implicit 0 times x squared. Right. So it's fine to not have its term in there. That just means its coefficient is 0. This one, again, like we have a sense of this. The degree to this will be 1. A1 is 2. And A0, the constant term, is just going to be 7. That's how we understand polynomials. If I were to give you, just to really make sure we understand that it goes both ways, if I were to give you A3 equals 7, A2 equals -2, A1 is equal to 0, and A0 equals 9. Who feels like they'd be able to write out the polynomial there? Yeah, so let's write it out just to make sure. That would be, the polynomial would be f of x is equal to 7x to the what for this one? 3, yeah. Exactly. That's A3, that's the degree 3 term. Minus 2x squared. 0, that means we can forget the linear term, plus 9. That's the polynomial represented by those coefficients. All right. So polynomials might be a little bit more familiar. Let's erase all of our cryptography now. And like, why are we looking at polynomials? We've seen them time and time again throughout our mathematical careers and education. And once again, math gives us structure. When you have structure, you can build things from structure. So we'll talk about a few properties that polynomials have. And next class, Thursday, we'll show, I think, some of the two coolest things in the discrete math portion of the class. How you can use polynomials to get some really cool constructions. So yeah, we've seen polynomials kind of our whole lives. So for example, a1x plus a0. This is a polynomial, but also it's a special type of polynomial. Anyone tell me what this polynomial is called usually? Yeah. A line. Yep. This sure is a line. You know, there's our slope. There's our y-intercept. Sometimes it's called mx plus b. We're using a1 and a0. But slope and y-intercept, if we have f of x is equal to a2x squared plus a1x plus a0, we usually call this a parabola. We've seen a bunch of polynomials in a bunch of different shapes. The names start to get less interesting, right? So this one is just called a cubic because, look, we're cubing it. a1x plus a0. This is cubic. And after that, you get quartic, quintic, and, you know, the names start getting less imaginative. But that's fine. And that goes down. The thing I want is how many points? That is for a line. Show me on your fingers how many points we need to uniquely define a line. Yeah, 2. If I have these 2 points, you can already see what the line is. It's that one. Yeah. So there's a line. So we need 2 points to define a line. If you had to guess, we haven't proved anything yet. If you had to guess, show me on your finger. Yeah, we do need 3. There's a unique parameter that passes through them. Cubic, again, at a guess, we might guess 4, 5 here. And this is for a degree 1 polynomial. This was for a degree 2 polynomial. Degree 3. And again, we haven't proved anything. We're just kind of making guesses. We're about to prove something in a moment. I had a polynomial of degree 100. X to the 100, and, you know, plus all the way to the constant term. If you had to guess, how many points would we need to uniquely define a degree 100 polynomial? 101. We'll prove that in a moment, and that's for degree 100. Okay. So kind of what we have here, just by guessing, is we can make a conjecture out of this. Did someone want this left up? All right. All right. So what we have here is a conjecture. Basically, the conjecture is d plus 1 points uniquely define a polynomial. And we're at, okay, we're making time. Great. So here's one conjecture. D plus 1 points. This is basically what we were just conjecturing up there. D plus 1 uniquely define degree D polynomial. This is something we're going to prove. And this is one of 2 properties of polynomials. We really only care about 2 properties, and that's going to give us so much. Like Thursday, we're going to use these 2 properties to do some pretty, some pretty cool things, actually. These topics are quite cool. So in the notes, I think the notes talk about this as being the second property. So this is property 2. Property 1 is another one. It's any non-zero degree D has at most d roots, or zeros. Okay, so these two properties, and we haven't proved them yet. We're about to in a moment. Where do I want to prove them? Yeah, I think we can get rid of them. So first off, property 1. The proof of property 1, we're not going to do. This is proof in notes, but I'll give you some intuition. Proof in notes. I'll give you some intuition, and I'll tell you how it's kind of what big pieces they use. And the intuition is this, you know. Let's say I give you a polynomial, f of x is equal to x squared minus 3x plus 2, and I ask, what are its roots? Again, what are roots? Roots are where the polynomial crosses the x-axis. So if I have a parabola, that poorly drawn parabola, but there's one root, there's another. Where it crosses that x-axis and becomes 0. So where is the polynomial 0? That's what a root means, that's what a 0 means. Sometimes they're used interchangeably, roots and zeros. But we're trying to find out where the polynomial becomes 0 by crossing the x-axis. So if I ask that for this, you might need to take a moment. You know, you could use the quadratic formula, however you memorized it, you know, negative b plus or minus square root of b, or like the negative boy deciding whether or not to go to the dance or something. However you memorized it, there's the quadratic formula, or you could factor. And this one factors nicely. This is x minus 1 times x minus 2. And the question is, when is that equal to 0? If you FOIL that out, you'll see that this is the same. So the question is, what are the zeros here? Show me on your fingers, what are the zeros to this polynomial? Yeah. In this form, it's a lot easier to see. We have x equals 1 and x equals 2, right? Because if you plug 1 in, 1 minus 1 is 0, that becomes 0. If you plug 2 in, you get 2 minus 2 is 0, it becomes 0. So the proof of this is just that if f of x has degree d, then you can always write, or you could basically always write, f of x as x minus r1, 1 root, x minus r2, all the way to x minus rd. So if you have a polynomial that's degree d, you can break it up into its roots. What's the degree of this? You have to kind of think about it for a moment, because what you're doing is foiling everything, just distributing all that. But what happens is you have d of these things being multiplied, each of degree 1. So the term is going to be x to the plus a bunch of things. You're going to have that x to the d, x times x times x, all of those. So this is degree d. And this is how you basically find out that a polynomial of degree d has d roots. The way the notes prove it is using induction and polynomial division. Just for time, and because it's not in the homework, it's just kind of like, it's only used to show the proof. It's not in the discussion, not in the homework. This is just used to show the proof. It's good to read, but the proof is polynomial long division to basically factor out, and shows that you can always kind of take a polynomial and start breaking it up into its roots like that. So we're not going to do a formal proof, but that's the intuition. All right. What we are going to formally prove is 2. So we're going to prove 2, and oh yeah, we're doing good. Great. So yeah, let's go ahead and prove 2 now. The proof of 2 is once again one of those special proofs where we're not just proving that it's true, we're doing a constructive proof. that is with d plus 1 points, we'll find out how to find that polynomial. So we're going to construct that polynomial from d plus 1 points. I can erase this? Yes, I can. Okay. So let's say I have points. Do the proof of 2, but before we do that, we're just going to look at an example to see how you would construct it. So let's say I have 3 points. 1, 1, 3, 4, and 6, 2. So if we plot this out, you know, we have 1, 1, we have like some 3, 4 over there, and we have some 6, 2. So maybe it's some parabola that looks like that. Poorly drawn, but again, we're just trying to find a polynomial that passes through those 3 points. So how do we do this? How do we find a polynomial that passes through those 3 points? We're going to interpolate them. We're going to interpolate them in a very specific way, and it should actually look a little bit familiar, because we're going to do what we called a magic trick before. And it still kind of is a magic trick, but we're a little bit more used to it. What we want is a polynomial that passes through, well, yeah, what we want, degree 2 polynomial. That's just, if we're trying to prove this is true, we're starting with 3 points, and we're trying to find a degree 2 polynomial from that. So how do we find a polynomial that passes through all 3 of these points? Well, the output of the polynomial should output what? It should output 1 at some point. It should output 4 at some point. And it should output 2 at another point. So what we're going to do is basically the same thing as Chinese remainder theorem. We are going to create radio buttons from algebra. Once again, we want to be able to select, not select the other 2, and then be able to select 4 when we want it and select 2 when we want it. We're going to, again, in a different way, because we're not doing modular arithmetic right here, we're going to use algebra to create a machine that you can select different, like a radio button, which one of those outputs you want. So how do we do that? Well, let's say I wanted to focus on the input 1 to 1, or when you plug in 1, what we want to output is 1. Let's just take a look at this for a moment. If I do this, if I plug in 1 to this polynomial now, what happens? So what happens to this term? Becomes 0. I plug 1 in, 1 minus 1 is 0, that goes away. This term, also 0. I plug in 1, it goes away. So if I plug in 1 to this polynomial, I get out 1. So far, so good, right? I plug in 1, I get 1, because these just disappear. We're creating a radio button. Okay, so let's keep going with that intuition, see if we could keep building this. Let's see. So now we want to plug in 3 and get 4. So what I want is I want 4. So if I put x minus 3 here and x minus 3 here, if I plug in 3 now, what happens to this term? Yeah.
It's sort of a question. But
Yeah.
if you plug in 1, wouldn't it be 1 plus 4 to the power of 0 plus 2 to the power of 0?
Great question. I'm writing this because we're going to be dividing by something in a moment. This is not an exponent. I should have made that clear. This is multiplication. So there's a multiplication there. Yeah, okay. Great. Thanks for that catch. We're going to be dividing something, so I just kind of staggered them a little bit because I knew what was going to be on the board. But yeah, these aren't exponents. This is 4 times x minus 1. This is 2 times x minus 1 times x minus 3. Okay, great. We're all on the same page now. So if I plug in 3 to this equation, what happens to this term? 0. 3 minus 3, 0. That goes away. What happens to this term? 0. 3 minus 3, that goes away. And now what happens if I plug in 3 here, I'm left with 4. But then, because this x minus 1 from before, now I get 3 minus 1, which isn't what I want. I get 4 times negative 2. So I just need to cancel that. So far, so good. If I plug in 3, that goes away, and what I'm left with is 3 minus 1 over 3 minus 1. Those cancel. We're good. But now we kind of mess things up. If we go back to 1, 1, now what happens if I plug in 1? If I plug in 1, goes away, 1 minus 1. This goes away, 1 minus 1. But now I get 1 times 1 minus 3, so 1 times negative 2. Problem, cancel it. So we're again kind of building radio buttons in the same way we did with Chinese remainder theorem. That is, we have something that when we multiply, it becomes 0 and just cancels everything out. But then we need to multiply by the inverse as well so that the whole thing becomes 1. So let's just write this out and see how it works. This is the intuition we want to build. Sorry, that's 6. So we have 6 minus 1, 6 minus 3. And we have the last one, we want to plug in 6 here. So I'm just writing this out, and then we're going to walk through it. And this is going to be 3 minus 6. OK. So now let's check it for each of these 3 points. If I plug in 1, this goes away, 1 minus 1. This also goes away, 1 minus 1. What I'm left with is 1 times, if I'm plugging in 1 here, it's 1 minus 3 over 1 minus 3. We're good. If we plug in 1 here, it's 1 minus 6 over 1 minus 6. So these cancel, and all we're left with is 1. That's what we want, right? When we plug in 1, we want 1 to pop out. When we plug in 3, we want 4 to pop out. Does that happen? Well, let's see. If we plug in 3, what happens to this term? 0, 3 minus 3. Same with this term, 3 minus 3. That goes away. And now if we plug in 3, we have 3 minus 1 over 3 minus 1. Those cancel. 3 minus 6 over 3 minus 6. Those cancel. And what we're left with is 4. We can do the same for 6. But this is the same basic principle as the Chinese remainder theorem. We are creating a series of radio buttons that let us choose 1, let us choose 4, and let us choose 2, depending on what we plug in. Any questions on that? Because we're going to see it in a general form now. Okay. So again, it's kind of this magic trick where it's like you want to interpolate it. Let's create radio buttons with algebra. This is how you do it. More generally, this is going to look a little bit more jargony, which is why we started with this. We can erase that. So let's do that. So what this is called is, well, it's interpolation, but it's a specific type of interpolation. Like many of these math theorems, it has some person's name attached to it. This is called Lagrange interpolation. This is the same Lagrange that I mentioned last time that had Lagrange's theorem about Euler's tangent function. People have their fingers in a lot of pies. So Lagrange interpolation is, let's say we have d plus 1 points. And those are going to be, let's just call them x1, y1, x, all the way to, yeah. Thank you. And then thank you. And now we're trying to create a degree D poly. A degree D polynomial. And how do we do that? It's going to be this radio button. F of x will be, we want it to be y1 at some point. We want it to be y2 at another point. And, we want this to kind of keep happening until we get to yd plus 1. And we just want to switch between which one we're doing. And the way we do that is with this gadget. Like each one of these is this special little construction. In the notes, it's called delta 1 x. And we're about to say what deltas are. Delta 2 of x plus, and then we get all the way to delta d plus 1 of x. This is going to be a bit jargony, and we're just going to have to stare at it and kind of look at it. But really, everything that's happening is what's happening up there. So what are these deltas? Delta I of x is defined as the product. This is product notation instead of summation notation, product notation. It's going to be the product of x minus xj. This is for all j not equal to I. We're just going to write this out and talk about it afterwards. The product of everything j not equal to I, and this is xi minus xj. Jargon, right? Just a big formal mess. But really, all it's doing is what we did up there, right? We're taking the product of all the things so that if I plug in some xj that's not I, then what happens to this whole product is xj minus xj, it all goes away. This is the radio button that turns off and on. So we want to do xj minus xj, but also if we plug in xi, we want all of these to cancel. We want xi minus xj to cancel. So it's a bit jargony to look at. You have to work through examples. You have them on your homework, so you'll work through examples. But really, this is just a real nice, compact shorthand notation for what we did up there. The real important part here is that this will be equal to 1 if x equals to xi. That is, if I plug in xi, it'll equal to 1. And if it will be 0 if x is equal to xj for any j not equal to I. The 0 is easy to see in the sense that take xj and plug it in. Well, at some point we get xj minus xj, and that becomes 0. It knocks out the whole thing. So yeah, again, we have to move fast. I'm sorry, but this is the construction. This is a gadget that we're using to kind of turn on and off which y1 and y2 we're using. It becomes, if we want y1, all the rest of these deltas become 0, and we select y1, and vice versa for all of them. It just kind of pops in and pops out. That's the reason why this is the generalizations, abstract and formal. Any questions on that? I know that's a bit much. So this is called Lagrange interpolation. This is the formal definition of what we do up there. The big question is, what degree is this? Right? So let's look at a concrete example. The one we just looked at a moment ago. What's the degree of f here? So I'm seeing some 2's. And, well, what's the degree of each one of these? We just have x times x, so this is degree 2. And each one of these is going to be degree 2, right? It's multiplying all the x's other than the one we're trying to pop in. So each one of these is degree 2, and if you add degree 2 polynomials, they're going to be a degree d polynomial. Right? So the way Lagrange interpolation works is we add up a bunch of degree d polynomials to get a degree d polynomial. So you can always do this. So why is this a proof of 2? It's because you could take any d plus 1 points, do Lagrange interpolation, and end up with a degree d polynomial that interpolates all of them. Let's see, do we have time to prove uniqueness? We might, but I'm going to do a quick diversion before we do that because I want to get to it. No, let's prove uniqueness. Okay. So I need a better shock. Okay. So we proved that a degree d polynomial exists. Now we want to prove that it is a uniquely defined polynomial. So how do we know it's unique? This is the proof. And this is how we always prove uniqueness. Assume there's 2. Show that they're actually the same. Right? So assume f and g degree Yeah, both of these are degree D polys passing through. And they pass through the D plus 1 points. Pass through those D plus 1 points. And what we want to show, WTS, is that F and G are actually one and the same. Right. So the way we do that, this is a pretty common trick. If you haven't seen it, here's your first time. It's to create a new thing, a new polynomial, P of x, which is equal to F of x minus G of x. If we can show that P of x is equal to 0, that means F of x and G of x are the same. Right? Like if this was equal to 0, I can just add G of x on both sides, and it just, oh, F of x is equal to G of x. So how do we show this? Well, if P of x is F of x minus G of x, what do we know? We're going to have to move fast, I'll just tell you. And that's P of x is going to be degree less than or equal to D. If you take two polynomials and subtract them that are both degree D, you can't increase the degree. So P of x is degree at most D. By property 1, we know it has at most D roots. Implies P has less than or equal to D roots. That is, less than or equal to D places that is equal to 0. There's a contradiction here. Anyone see it? So how many places, it says the amount of things that equals 0 is D. But that can't be true because F and G agree on D plus 1 points. It can't just agree on only D points because F and G both pass through the same D plus 1 points, which means P of x is P of x is F of x minus G of x will be 0 on D plus 1 points. And that's a problem. So has less than or equal to D roots, which is a contradiction. It can't have less than or equal to D roots because they agree on D plus 1 points, so P of x better equal 0 on all D plus 1 points. And the thing that happens with that contradiction is the only way that could happen is if this gets violated. That is, P of x must be the 0 polynomial. Yeah, so if P of x is the 0 polynomial, then F of x minus G of x must be the same. So we want to move on to the next thing, and that was fast and a bit hand-wavy. Any questions about that before I do the last thing I want to do to prepare you for homework? Okay, great. Last thing to prepare you, this will go pretty quick because you know it all already. I'm going to ask you a quick question here. And which polynomials are the same? Here's 4 polynomials. 3x to the 5th minus 2 and x. Which polynomials are the same? Trick question, none of them are. Look, they're not the same. Okay, which polynomials are the same mod 11? This polynomial and that polynomial is the same mod 11. They have different coefficient representations, but they all equal the same thing. Why? Well, because right there, x to the 81 is congruent to x mod 11 by Fermat's little theorem. So we can do polynomials over modular arithmetic as well. You're pretty familiar with modular arithmetic, and that'll be on your homework, but we're not teaching anything new. You're just going to do modular arithmetic as you've always done it, except now you have polynomials in place. So you can do that. One thing I want to note is I've been talking about ZP, that is 0 to p minus 1. The notes calls this the Galois field of size p. So just know that anytime it says Galois field p, it's talking about what we've been talking about as ZP. Galois fields are important because it means your multiplication works well. It means you're working over a field. Well, we haven't talked about what a field is. Oh, we have time. Great. We haven't talked about what a field is. But a field is just where multiplication works out well. And we see this. With mod p, that's where we have multiplicative inverses, and you can kind of cancel things as you want. So, oh, I did erase it. Okay. So remember when I asked what the roots are to this? X minus 1 times x minus 2. What are the roots that make this equal to 0? These are easy to see. Well, it's x equals 1, and it's x equals 2. But let's say we're doing this mod 6. Here's a trick. X equals 4 also works. Why? Let's plug it in. 4 minus 1 is 3 times 2. 4 minus 2 is 2. That's equal to 6, which is congruent to 0 mod 6. It's a problem. This is called 0 divisors. 2 and 3 are 0 divisors. They multiply to 0. And that creates a whole bunch of mess. Because what it does is it breaks property 1. This is a degree-2 polynomial. It should only have 2 roots. And here's 3. At least 3. So the reason why Galois fields are so important is because if you aren't working over a field, that is, if you're working with something that doesn't have multiplicative inverses, 2 and 3 don't have multiplicative inverses mod 6 because they share factors, you get all this weird stuff that happens. Your properties no longer hold, everything breaks. So this is why we always work mod p. So that's just a thing to watch out for, that, or just to know, like, why do we do all of our polynomials over the Galois field of size p? It's because when you don't, you can't do algebra like you expect. Your properties break, you can't cancel, you don't have multiplicative inverses, everything gets real messy. So what you'll have in homework is just working with polynomials over modular arithmetic as well. Yeah? P could be any prime. I should have said that. P is, and the point is, if P is not prime, you get weird stuff happening here. And then you can't do algebra anymore. And I think we're at time? Yeah, we're at time. Okay. Yeah.